I'm saying they're both resting on the y-axis, and this was also conventional. I don't think it. Yeah, but I just don't know where it might rest. So I don't know. It's just really pushing everything. I don't think it. I think it just keeps going down. So we got how to explain this law.
Okay, so let's take a look at these things and see what we can figure out. Way back at the beginning of the semester, when we first started talking about graphing functions, there were, half a dozen things, and we just sort of drew them. We're like, okay, well, that thing is always shaped like that, or, absolute value is always shaped like that, right? Now, with the polynomial stuff that we just came out of, we kind of had to let go of that idea a little bit, right? Because there's more going on, right? Depending on what's going on, right? We did some that, turn 3 times and the multiplicity and, all this different stuff. That's going to be even more true here, right? We have to let go of the idea that like they're always going to look like, anything, because these are 2 polynomials, which are already like more complicated. We're dividing, we're combining them together. So there's going to be more like variation in the shape and stuff. And that's okay. There's going to be some stuff that we can figure out at kind of low cost to us, right? Stuff that we can figure out by looking in the right place to get the information that we need for what we're going to do right now. This is a thing that we can go, pretty far down the rabbit hole. If you go on and take Calc 1, you'll revisit this idea in a lot more detail. For us, we're going to get what we can get using the stuff that we know, and we're going to be happy with that, basically. So here is 1 over x. What do you notice about this thing?
It does not have any sort of, it's just x by itself on the bottom.
Okay, just x by itself on the bottom. So just 1 divided by just the variable x, nothing else going on. Like I said, this is about as simple as we can make that part to get it to do like interesting stuff, right? Okay, what about the graph? Okay, so and what that means is that there are places where there's a like a break or a disconnect. Discontinuity is the math word in the graph where it sort of separates. So just thinking about it like pictorially, right, what it looks like, hopefully the thing that jumps out at you first is that it's in 2 pieces, right? There are these 2 separate branches that are disconnected, that don't, meet up, they don't touch each other. That's weird. That's different than anything we've looked at before. Up to this point, anything that we graphed or looked at, you could draw as one single piece, right? Meaning it's continuous everywhere. That's not true here. If I'm going to draw this, I would have to lift my pencil at some point, which means it's discontinuous. Okay, similar sort of thing happens here. Similar, but even more so happens here, right? I think I heard one of you guys say something about like this one's all over the place, right? This is in 3 separate chunks, right? So there's 2 places where it sort of breaks apart into different pieces. That's for the moment, the thing I want us to kind of notice most of all is that often these are going to be like that, where they're sort of disconnected into, discrete separate pieces. Okay. The other thing about what Grady said about the asymptotes is that these lines that, sort of the further off I go to the edges of the graph, the more the curve starts to sort of settle in and look like that line, right? So I'm going to kind of zoom this thing way, way out. Yes, it's in one way and out the other way. So what we're looking at right now is a really, really tall but narrow strip of this thing, right? I zoomed way in on the X values and way out on the Y. So we're in the like, this is 100,000, 200,000. We're looking really, really tall but narrow. And what do you see? The picture doesn't really look all that different, does it?
It does not cross the y.
Yeah, it doesn't actually cross the y-axis. The further out I go, the more I have to kind of zoom in to see the difference. But this is always sitting just outside of the axis, right? Just off of it. And the same thing's true here. And if you go out further, you zoom in more, you still see that separation. Okay? Why does that happen? The y-axis would be approaching y-intercepts would mean approaching x equals 0, right? What happens to this? Where's something I can point with? What happens to this function if I try to plug 0 in? It'd be undefined, right? 1 divided by 0. Anything divided by 0 is bad news, right? It's undefined. Division by 0 is not an operation you can actually do, right? You have one cookie and no one to share it with. And that's sad, right? So this is an undefined operation. That means I can't evaluate this function at 0. That means it doesn't have a y-intercept. But what happens is that for numbers close to 0, you get back something really big, right? If you divide by a really small number, you get back a really big number. That's why this thing sort of shoots off to infinity like it does, the closer we get into the y-axis. Okay, so sort of keep that idea in mind and look for that same kind of thing happening. What does this one do? 1 over x minus 2.
It shifts the graph to the right.
The same thing, it just shifts the graph to the right. This is taking the function we started with. Think about your transformation stuff. Where there was an x before, I replaced it with x minus 2, right? That's like putting x minus 2 inside the function, right? Inside the parentheses, if you want. That shifts everything to the right too. So it's the same thing, just shifted to the right. This one, again, more going on, right? Graph is weird, doesn't look all that much. You know, there are kind of pieces of it that look sort of like those last couple, but apart from that, there's a lot more, you know, variability in what's going on. But do we see the same kind of behaviors happening anywhere? Can we spot places where, you know, I kind of can imagine sort of squeezing a line in that is sort of showing what's happening? There's a place where the graph kind of breaks apart right here. And near that break, again, I can kind of imagine like how a line would fit in there, right? This grid line that's on the graph kind of shows it to you too. And there's another place over here where the same thing happens, right?
Is that on the x-axis?
Yeah, and there's also the same kind of thing happening, you know, sort of horizontally with the ends out here and out here. We'll come back to that too. First, though, I want to focus on the thing we kind of always want to focus on first for a function, which is where does it even exist? Like, where does it make sense to talk about it? So looking at 1 over x. Just sketch it real quick. Something like that. What'd you come up with for its domain?
Negative infinity to 0, u 0 to infinity, and it's all parentheses. What's
the one place where 1 over x would fail to exist, would not be defined? 0, right? F of 0 would be 1 over 0, which is still undefined. So just in English then, what's the domain for this function? Everything except 0, right? 0 is the one place where there's a problem, the one place where there's trouble. Bad stuff happens when x is 0. If x is any positive number, it's just 1 divided by a positive number. That's some positive number. That's fine. If x is any negative number, it's 1 divided by a negative. That's negative. That's fine. 0, though, is undefined. 0 doesn't work. So the domain is everything except 0. Okay. Everything except x equals 0. Now, how can we write down everything except x equals 0? Say that one more time.
Parentheses, negative infinity to 0, mu, parentheses, 0 to infinity.
Parentheses mean you take the open interval, which means you can go right up next to the number, but not include it. So everything, the whole real line would be negative infinity to infinity, right? Okay, so what I want is from forever, right? Negative infinity all the way right up next to 0. But then I got to skip over 0. The way I skip over it would be to take the open interval to the left and then the open interval to the right and then union around it. So the only thing I'm leaving out is 0 itself and then continue on to positive infinity. That's how you write everything except one point is you union around it with open intervals like that. Does that make sense? Another way you could write that in set builder notation would be something like this. The set of x so that x is not equal to 0, right? That says the same thing. We're mostly going to stick with interval. Well, maybe exclusively. I don't think it comes up anywhere in the homework, but you might see it if you were like reading something. That means the same thing, right? It's everything except for 0. That's a not equal to right here. Okay. That's just another way to write the same thing for the domain. Yeah. Okay. Now for the range, so the y values, answer the same question, but sideways, right? Looking at the y values, what do you see?
Same thing.
Same thing. Yeah. The range, basically now we're asking where is 1 over x equal to 0, right? And it's not, it doesn't. X can't be 0 because that would be undefined. If it's positive, then this is positive. If it's negative, then this is negative. There's no way for it to be 0 then, right? So in the range, we have to leave out or skip over or, exclude 0 for, kind of the same, but turned on its side reason. So what about the x and y intercepts then? There are none. It doesn't ever cross the coordinate axes, right? It gets close to them, doesn't cross them. That means there aren't any intercepts. So what it does do is gradually curves toward or approaches the x and y axes. But without ever crossing. There's a word for that. Those are called asymptotes. And we're going to be spending a lot more time on developing this idea. But okay. So if that's how 1 over x works, and again, there's going to be a lot of, there's a lot more like variation in how these things work. So we're not going to be able to do it as just, shifts of that all the time. They're not all going to look like this, but these same kinds of behaviors where there are places where the thing is undefined. So there are things we have to leave out or exclude from the domain. And those are places where it's not continuous. And sometimes this kind of thing happens. So the behaviors are going to be the things that kind of get repeated or that come up again and again. Not necessarily like the same picture though, right? Okay. 1 over x minus 2 though, that is just a shift. That just takes 1 over x and shifts it to the right too. What does that mean about the domain then? It's everything except for 0 was a problem before. We moved everything to the right 2, so everything except 2. How would we tell if I didn't spot, because maybe you didn't, if I didn't spot that this is a shift to the right from that function that I already know about, right? What if I just take a look at this thing and treat it like it's its own thing instead of trying to compare it to something else? How would I identify that 2 is going to be where there's a problem? That's where the denominator would be 0. We've done this a little bit before with like square roots, and we'll revisit that idea in a couple of weeks, but we'll see this come up in some other places too. A lot of times to figure out where a function is defined, we can figure out instead where it's not, like where bad stuff would happen, where there would be problems. Here that means dividing by 0. If x is 2, this would be 1 over 0. 1 over 0 is undefined. So 2 is a place where bad stuff happens. Right? At 2, it's undefined. That means the domain is everywhere except for 2. Okay. What about the range? Same thing, right? We took the whole function that was, that never crossed through y equals 0, and we moved it to the right. That doesn't change the range. If you want to think about it another way, if I tried setting that equal to 0, there's no way to divide 1 by something and get 0, right? If you have 1 cookie, it doesn't matter how many people you share it with. Everyone gets some, right? So there's no way for this to be 0. That means the range is everything except 0. That also means that there are no x-intercepts for the same reason. Is there a y-intercept?
Yes, it's 0.5 because that's going to be 1. Well, it's actually negative.
Yeah, how do you find a y-intercept? You let x be 0. If you plug 0 in, you get 1 over 0 minus 2. So the y-intercept is 0, negative 1/2. Okay. We'll come back to the asymptote thing. Sorry, we'll come back to the other interesting stuff. I wrote the notes. I don't like reveal the asymptote thing until later, but then it comes up talking about it. More going on here, right? Saw the graph. It's weird. There's a lot going on. It's sort of in 3 separate chunks, right? But how can we figure out the domain? Where does bad stuff happen? What does bad stuff mean here? For a function that looks like this. 0 where? In the denominator, yeah. Okay. So what we want to know then is, where is this equal to 0? Oh, hey. That just means we just need to solve a quadratic, right? Oh man, it's a good thing we know so much about solving quadratics. You thought you took a test and it was going to be gone forever. Not so fast, my friend. We figure out where the denominator is 0. We figure out where the fraction, the division question would be undefined. That tells us then what needs to get sort of kicked out of the domain. So where is that equal to 0? Factor, quadratic formula, we got to solve it somehow. Multiplies to -6 and adds to -5. X squared minus 2x minus 3x plus 6 though.
6 and -1.
So let's try 6 and 1. -1 and plus 6. Okay, so that would be minus x plus 6x minus 6. So that'd be plus 5 in the middle. So we need to switch the signs. So plus 1 and minus 6. Which makes this plus and minus and that minus, and that's what we wanted. Again, if you want to do quadratic formula, that's fine. These should be, you know, for the most part, if the denominator is quadratic or something. Oh, well, sometimes I'm going to give it to you already factored, but if it's not already factored, then it should be something that's fairly, you know, painless to go find the zeros, whether you do it by factoring or by quadratic formula. So what are they? -1 and 6. So in other words, if I try to take x equal -1 and plug it into that, I get -1 plus 3, so 2, over 1 plus 5 minus 6, so 2 divided by 0, which again is bad news. Same thing happens with 6. What's the domain then? It's everything else. Everything except those 2 points. How do you write everything except those 2 points?
So it's negative infinity to it's to infinity.
Start with everything before -1, right? So -1 and 6 on a number line would be in that order, left to right. So start with everything before -1, and then everything after -1 until you get up to almost but not quite 6. And then skip over 6 and take everything after. Okay, so 2 discontinuities, 2 places where it's undefined, means that you take the whole real line, the whole x-axis, and chop it into 3 pieces. And that's what those would look like as intervals, right? It's just unioning around the like bad point, right? The place where it's undefined by taking open intervals on either side. Is everyone okay with that idea? Again, like pretty much anytime we deal with a rational thing, that's going to be the first thing you want to do is, you know, even if we're not going to use it or you're not asked about it directly about the domain, you probably want to somewhere think to yourself or make a note or something about places where it doesn't exist, places where it's undefined. That's by looking at where the denominator would be 0. Okay. Now the range thing, that just got harder. We're talking y values, right? Well, the others that we've looked at, it was not really all that bad because you had these 2 separate pieces, but they kind of almost lined up with each other in terms of what they did for both the x and the y. What's different about this? There's this big chunk that's missing. right? There's this whole chunk right here that, I don't know, maybe if I go out further here, well, nope, doesn't look like it comes back down or picks that up anywhere, right? So there's this big hole in the thing that's, just missing, just this chunk that's deleted. Desmos will tell me how low and how high those things get, and woof, it's some weird decimal thing that I don't really even know where this came from, right? So the range question just got a lot harder. And because of that, we're just not gonna worry about it. So we're just going to kind of forget about that for the moment. We can still identify it, sometimes, but not always. Again, there's a lot more variability in what happens with these, and it's not always clear how this connects to other stuff. You kind of need about a semester's worth of calculus to really be able to dig into that question. And we don't have that, so we're not going to worry about it. What we're going to focus more instead on is what happens to the edges, the ends of the graph. So ignore the middle. What do the ends look like they're doing? Here and here, as we go off the ends of the graph, how would you describe what those do? We did it before with arrows, right? For polynomial stuff. Said, it goes up or it goes down. How would you describe it here? Level, sideways, right? What this appears to do is level off that end a little bit above the x-axis, this end a little bit below the x-axis, but the x-axis is in common to both, right? That's where it's leveling off. So I can kind of imagine how I could fit a horizontal line in there at the x-axis that shows what the ends do, even if it doesn't give you a good picture of what happens in the middle. Make sense? So instead of focusing on the range, we're going to focus more on that aspect of it, looking at the describing the end behavior in terms of the y values that way. Okay, does it have any x-intercepts? Yes. Where and how do you know? Say again? Okay, there's one on the left side, yes. How would we go find it? Where do x-intercepts happen? The x-axis, so when y is 0, right? If you set that whole thing equal to 0, where would that happen? What has to happen for a fraction to be 0? It has to be 0 divided by something. It can't be something divided by 0, right? Something divided by 0 means you have one cookie and no friends. And regardless of the cookie status, you're very sad because you have no friends, right? 0 divided by something, 0 cookies, sorry, but at least you have a friend. But how much cookie does each friend get? None. 0 cookies per friend, but at least you still have a friend, right? Friendship makes the world go round or something. I don't know how to tie this together, but the only way for a fraction to be 0 is if the thing on top is 0, so that you're dividing 0 by something. That would mean that x plus 3 must be 0. So -3. Flip over to my graph. -3. Hey, there you go. And that's the only one. So x-intercepts always happen when y is 0. Here, y being 0 means the whole function is 0, means the numerator's got to be 0, because that's the only way to make a fraction 0 out. So the y-intercept, or sorry, the x-intercept, my bad, looking at the other thing, the next thing, is -3, 0. How do you find a y-intercept? y-axis, so x equals 0. You plug 0 into this thing, what do you get? 0 plus 3 over 0 minus 6. You get -1/2. Yep. So 0, -1/2. Okay. So there's a lot of individual little things going on here, right? And we'll, continue talking about like how all this stuff kind of fits in together. Again, none of the individual, like we're looking at the things that are kind of easily available, right? If we know where to look, right? None of these things require me to do a whole bunch of work or, know a whole bunch of calculus or something like that. It's all kind of right there. We just need to make sure we're looking in the right place. We'll continue talking about that. For the moment, though, the things I really want to focus on are the domain and this idea of where asymptotes come up. So let's just take a look at a couple more from a graphical perspective, right? Just kind of getting this information from the picture. Here are two functions. I want you to take just a minute to find the domain and any asymptotes for each of those things. Again, the asymptotes are, straight lines where the thing is sort of breaking around it, right? So before we talk about it all together, you just take a second and write down what you think they are. And these are totally different, brand new functions, by the way. These are not things that we know where they came from, apart from just the graph. What do you see in the first one? Domain, X values, what's included, what's not. What do you see? For the domain? What about -2? Okay. Think about it this way. If I crush that whole thing down onto the x-axis, this whole piece falls along here. This whole piece falls along here, but what gets left out? 0, right? Nothing lands along the y-axis, because what's happening near or at the y-axis is that one end's going that way, the other end's going that way. They're again sort of curving in toward it, or approaching that line without crossing, though. there's a vertical asymptote there at x equals 0. And what that means is that the domain does not include x equals 0 because it doesn't cross that line. It approaches, but never actually gets there. So the domain is everything except 0. Okay. Is there anywhere else that we can see a line that again kind of describes, the behavior of the function nearby? There's a horizontal asymptote. Where, Micah? At -2. It's a horizontal line, so y equals -2. That is this. The vertical one is this. Asymptotes are not exactly part of the function itself, right? That's why I've got them, drawn in like a different color and as a dotted line here. They're not really part of the function. Like I can't plug 0 into this function and get something back. When I get back, it's undefined. But that line at x equals 0 does show me what it does, right? So it's more like a guide or like a frame or something for what the function does nearby. Yeah, we'll talk more about asymptotes, but for the moment, just identifying them. So what do you see here? There's a vertical asymptote at x equals -2 and at x equals 1. I'm going to stop writing out all of the words and just abbreviate vertical asymptote. X equals -2 and x equals 1. What about a horizontal one? At 0. So y equals 0 because it's a horizontal line. No, I'm sorry. Okay, if there are vertical asymptotes at x equals -2 and x equals 1, what's the domain? It's everything else. How do we write down everything but those 2 points?
Wouldn't it be like -3, -2?
Yep.
-2, 1.
Yep.
And then 1, 2, infinity.
Yep. Everything else. Right, take the whole real number line, -infinity to infinity, just erase those 2 points. And again, this is the way you do that, right? With this union of both intervals. Okay, is there anything different or unexpected that happened with that last one, that second graph in particular? Anything about that I don't know, jumps out at you? What about it? Okay. Most of you can't see, Jamel's doing this. That middle chunk of the graph, right? This middle section, what happens? It goes through that horizontal asymptote right there, right? Okay. There's a little bit of a weird thing here, right? That like feels a little strange. Asymptotes, we use the same word because that's what that word means. This line that the thing's curving in toward. And they look the same. We draw them the same way, right? Just vertical versus horizontal, but they mean different things and they come from different places. The vertical ones are happening because those are places where We would divide by 0, only we can't because that's an undefined operation. But when you divide by a thing that's almost 0, you get a really big number back, right? Think about like 1 over x, the one that we started with. If I take 1 divided by 0.00001, I get back some huge number. And the closer in I go, the bigger and bigger that value gets. That's why the thing goes off to infinity like it does. The same thing's happening here. Those vertical asymptotes, though, those are like, that's like a steel barrier, a brick wall. Like, you can't go through that. You have to kind of go over it. That's why we do, that's what this is, right? This is like going over the thing. Because you can't go through it, you can't evaluate the function there. It does not exist along that line at all. Horizontal asymptotes are a different thing. Horizontal asymptotes are really just applying to what happens at the end, right? Think about kind of looking just along this line. The further out I go, the more it kind of looks more like that, right? If I look like this direction and that direction. This horizontal one, though, it does that at the ends, but it doesn't really give me a clear picture about what happens in the middle. So horizontal asymptotes are more about end behavior. So when we talk about end behavior, it's just kind of another option, right? It's not that the ends have to be pointing either up or down, and we need to figure that out. It's that there's this third option now that they could be just kind of level. But again, it doesn't really give me a clear picture of what happens in the middle. You can cross over those in the middle. It could, you could have a thing where it kind of just like wiggles back and forth along that line, but kind of converges and closes in on it. But it can go across those is the point. But it does kind of close in on them. We will talk, well, we got just a second. Okay, no, we don't. We'll pick up there tomorrow. Between now and then, these last 4 examples, take a look at those. You graph them if you wish, but try to think about answering these same questions, particularly finding the domain and identifying the vertical asymptotes. Okay, think about those. We'll pick up there tomorrow. Y'all have a good day.